talk about, the construction of gamma factors for model representations of GLN of FQ. So this is joint work. I say in progress because it's not public yet, but it will be in about 2 weeks. With Jackson Bakeberg, Mathilde Gerbelli-Gauthier, Heidi Goodson, Gil Moss, and Robin Zhang. So the way that I wanted to give this talk was to just start by giving a kind of like broad overview of gamma factors in the context of the Langlands program. And I guess in the context of like a finite field analog. But let me first start by just kind of reviewing and just going over what happens in the context of local fields before switching to the context that we care about, which is for finite fields. So yeah, the role of gamma factors is to give a characterization of the local Langlands correspondence. So let me fix a finite extension of QP, call it F. So then, okay, one way of stating the local Langlands correspondence, at least after you restrict to the supercuspitals. So this goes back to work of Harrison-Taylor, Iyengar, and more recently reproven by Schulze. But the way that I'm going to characterize it is more in the spirit of these two rather than this third proof. So yeah, so there exists a bijection. Okay, well, there exists a family of bijections, one for each n. Which I'll call LL, which go from, yeah, so I'm just going to restrict to irreducible, admissible, supercuspidal. So all of this is over the complex numbers, reps of GLN of F, and lands in irreducible, continuous, n-dimensional representations of the Vega group of F. Okay, so there exists such a bijection, and it's characterized by a list of properties, one of which I'll care about in particular, but let me list them all briefly. So characterized by the fact that it preserves so, okay, you want it to preserve, well, okay, for n equals 1, okay, this is going to read very well, but for n equals 1, it is given by class field theory, local class field theory. It's compatible with, so it preserves twists by characters, duals, preserve central characters, and what else do I want to say? Right, and then the thing that I most care about is that it preserves L factors of pairs and epsilon factors of pairs. And all of these things together characterize the correspondence. So in other words, if you take a pair of representations, pi1 and pi2, possibly of different dimensions, then the L factor should be the same as the L factor of the tensor product of the corresponding Vega parameters. And similarly, so you can state this either in terms of epsilon or gamma factors, but since I care about gamma factors, let me say it that way. So it also preserves gamma factors of pairs. Okay, so the uniqueness, the characterization by these L and gamma factors are equivalently epsilon factors was proven by Henyart, and the proof uses something called a converse theorem. So let me just state that converse theorem. So yeah, I guess theorem by Jacquet and Langlands for n equals 2, Jacquet, Piatetski, Shapiro, Shalika for n equals 3, but then let me just say Henyart for general n. Right, so this is this converse theorem, which says that if you assume that pi1 and pi2 are two supercuspitals as above, and you know that the gamma factor, so I haven't said what a gamma factor is yet, but I'll say what I mean in a minute. So if you know that the gamma factor of pi1 and pi2 paired against any other tau, where tau now runs from runs over all I guess irreducible admissible supercuspitals. So this is enough to so yeah, I guess you want this for just all the lower dimensional representations. So let me say supercuspitals of GLR of F, where R runs from 1 to n minus 1. Then that's enough to say that the two supercuspitals you started with are actually isomorphic. A remark is that there are sort of many versions of the theorem, and the optimal one, so optimally, you can restrict the range of, I mean, these R's, like in the way that I've stated it, they go from 1 to n minus 1, but you can restrict to just 1 to the floor of n over 2. So this was conjectured by Jacquet a long time ago and proven more recently by Liu and Jacquet. Okay, so right, so I've said that the correspondence is characterized by these gamma factors. So maybe I should say, if you're not familiar with them, what they are and how you define them. So I won't define them in full generality, but I'll give an indication of how you do this just for the case of GLN and GLN minus 1, because the general formula is kind of similar, but the integrals you need are a little more complicated to write down. So right, so suppose R, which is the dimension of tau, is n minus 1 as over there. So right, so the L factors and the epsilon factors are both defined using like a bunch of integrals taken, like you integrate a bunch of Whittaker functions. I mean, one way to, yeah, this is one way to do it. So I can define, so okay, since pi and tau are both supercuspital, they're generic, and so I can replace them with their Whittaker models, which I'll call W, curly W and curly W prime. They're Whittaker models. And so then we define a bunch of integrals of the following form. So let me just say that the L factor, L, I guess pi1 times tau, or maybe, yeah, pi times tau S, is in some sense the GCD of a bunch of integrals of the following form. So I take two Whittaker functions, one from each Whittaker model of each of these representations. And now, yeah, I'm assuming again that the dimension of this is n and this dimension of this one's n minus 1. So I integrate over GLN minus 1 mod the unipotent radical of the standard Borel. And then I take W and I sort of embed GLN minus 1 into GLN and then evaluate it on W. So W is now, well, I'll write this in a minute, but it's now a Whittaker function for, yes, sorry. Yeah, that should be F. Yeah, thanks. Okay, times the norm of the determinant character. So okay, there's some exponent which depends on the difference in these dimensions, but in this case, it's just a half integrated with respect to a Haar measure on GLN minus 1. Yes, thank you. Okay, and yeah, and here, so you kind of range, you kind of vary this over all Whittaker functions in the Whittaker model of pi and all Whittaker functions in the Whittaker model of pi prime. Okay, so this is how you define the L factor. I mean, really more precisely what you do is you say, okay, these integrals as I've written them if you make the variable substitution q to the minus s is equal to x, then these define sort of like Laurent series in this variable x. And then you can look at the ring of Laurent series, and you can look at all of these gamma factors. They generate an ideal. That ideal is generated by something, which is called the L factor, or by definition. And then, right, so then the definition of the gamma factor is as a constant of proportionality between two integrals of this form. So in the n-1 case, it's sort of easier to write down these two integrals. So I'll just stick to this case. Right, so the gamma factor is the constant of proportionality between, well, so you sort of take the integral I that I just defined up there, and then you dualize everything, and then you write the same integral. So you put 1 minus s and then w tilde and w prime tilde, which I'll say what that means in a minute. But yeah, so this by definition, so okay, it's not clear why you can define it this way, but I'll say in a minute what the key step is to do that. Right, so it's the ratio basically up to the sign of the central character. Sorry, this should be tau. Up to the sign of the central character of tau. It's like the ratio between this integral that I find up there and then the integral of the same thing, but now you sort of dualize. And yeah, so maybe I should say, so w tilde is a Whittaker function for like the dual representation, the contragradient representation with the additive character switched in the Whittaker model. And this you can define by just taking the conjugate transpose of G, which I'm just gonna write as iota, and then multiplying on the left by the longest element of the Weil group, and then evaluating the Whittaker function on that matrix. And then, okay, the same thing is true for W prime, but this n becomes an n-1, but otherwise it's the same formula. Okay, so, okay, why can you do this? I mean, the point is that, so to get existence, you need to, so you can reduce this to showing that the space of, let me say, GLN-1 F equivariant bilinear forms on the Whittaker spaces. So on, let's say, W times W prime to just 1. So this is the trivial action of the group. Is a one-dimensional C vector space. Okay, so this, what I've just described, this definition in both of these definitions, these are due to Jacquet, Piatetski, Shapiro, and Shalika in a paper called Rankin Selberg convolutions. And the proof, the proof of the one-dimensionality of the space of bilinear forms, although they don't write it in exactly this language, follows from, or you can write the proof by using properties of the so-called Bernstein-Zelevinsky derivative functors. So they introduce these functors which move you between representations of GLN and representations of a mirabolic, and then representations of a mirabolic of a smaller degree. And if you know enough about these adjunctions, and you can reduce the space, like studying the space of bilinear forms, to something much simpler, and then kind of conclude its rank 1 pretty easily from that. Belavinsky, yes, that is not a name. Thank you. Good point. 1 second. Also need more chalk. Bernstein Zelevinsky. Thank you. There are two people, not one person. Okay. So yeah, any questions so far? This is kind of a review of very old math, so cool. Okay, so that's kind of what I want to say about the case of local fields in characteristic 0. So now I want to say something about the modular setting. Okay, so in the modular setting, so we still care about so yeah, the modular representations of GLN of F. So I still care about the same p-adic local field. But now I'm going to take the coefficients to be FL bar. So L for me is not P. So I'm looking away from P. So the construction of a model like local Langlands correspondence was done by Iyengar. And she constructs a full correspondence, but I'm just going to restrict to the semi-simple one and reinterpret it as a generic correspondence just to, for simplicity and for my purposes, I guess. And so the way I'll write it is call it V, and it goes from irreducible, admissible, generic FL bar representations of GLNF to the I mean, you can take an irreducible admissible generic representation and you can ask for its supracuspidal support. So let me just write supracuspidal supports of such things. And this is a bijection. And then Iyengar constructs a supracuspidal model local Langlands correspondence, and then you can apply that to get a semi-simple n-dimensional representation of the Bakeberg group, but now with FL bar coefficients. Okay. So this correspondence, I guess maybe so like I spent some time talking about gamma factors. So the gamma factors in the characteristic 0 setting characterize the correspondence, but in the mod L setting, the first characterization given was by Iyengar was a compatibility with the with the characteristic 0 correspondence, which is to say that if you sort of switch from C to QL bar, and then you take those supracuspidals which are integral, so they admit like a stable lattice, and you reduce and semi-simplify, then doing the Langlands correspondence and then in characteristic 0 and then reducing should be the same as reducing and then applying this correspondence. And that determines it uniquely. But you can ask, are there, or maybe I should say, is there a characterization in terms of local constants? So like, maybe an L factor, gamma factor, etc. And the answer is sort of yes and no. So let me explain what I mean by that. So this is this is slightly out of order, but sorry, just give me a second. Korinchuk and Matrange. Well, actually, okay, before I say this, maybe I should say a word about what Vignard does. So you can try, okay, basically the point is that you can try to define, you can try to define gamma factors in the same way. You can define L factors and gamma factors in the same way. Meaning you can, take the analogous notion of integral in this setting, take the collection over all pairs of Whittaker functions, and then you can, see if they generate an ideal, and then show that like a space of bilinear forms is one dimensional, and find some kind of constant of proportionality. And so this is done like for GLN somewhat recently by Korinchuk and Matrange. But it was already realized, I guess, by Vigneris that this is, if you do it this way, you won't always get a converse theorem, and you won't even necessarily get a compatibility between the gamma factors that you define like this way and like the Deligne gamma factor that you get on the other side for the Galois representation. So neither of these things are true. And it's yeah, maybe I won't like write it out because of I don't have that much time, but the it's easy. You can write down examples. You can write down examples of, well, let me say, for instance, you can find a supercuspidal representation and a cuspidal non-supercuspidal FL bar representation, which are, well, not isomorphic, but they have the same gamma factor. And actually, Moss writes down like an explicit example and kind of proves that they have the same gamma factor. He does this in the case of it's like the simplest possible case, really. He does it when the residue character, the residue, the size of the residue field of F is 5, P is 5, L is 2, the group is two-dimensional. So yeah, in the simplest case, you can write down an example. And because it's in such a simple case, you can actually compute everything by hand using Gauss sums and et cetera. So it's, yeah. Okay, so I guess the upshot is that you can't use these gamma factors to necessarily characterize this correspondence. On the other hand, the same authors who define this gamma factors in full generality give a modified V. So by V, I mean Vigneris's model correspondence. So they take the semi-simple n-dimensional Weil representations that you get, and then you embed them into the bigger category where you don't require the n operator and the Weil representation to be nilpotent. And then if you do this properly, you can at least make the gamma factors match on both sides. Okay, but they don't prove a converse theorem because, again, there are counterexamples. And I guess the other thing I wanted to say is that Vignera has a strategy, just in the case of n equals 2, has defined, I guess, I think she calls them a new epsilon factor, which is sort of like a collection of epsilon factors or a collection of numbers or a collection of such. Let me just say a collection of epsilon factors. And this collection gets bigger whenever you have congruences between Q and 1 mod some power of L. So whenever there's a collection of epsilon factors of size 1, if Q is not congruent to 1 mod L. But the way that this construction goes is sort of by lifting to an integral representation, and then taking the epsilon factor in characteristic 0 and then reducing. And using this, you can prove a converse theorem, but only in the case of n equals 2. And there was a remark that a similar strategy might work for n equals 3, but then for n equals 4, I guess it gets complicated and nobody's tried this. Okay, so on the other hand, Moss has a solution to this problem of defining a converse theorem for this particular correspondence V that I wrote down. But it involves kind of enlarging the number of representations that you need to define, A, define gamma factors for, and B, assume are equal on both sides. And I guess the motivation is that if you look at the, if you sort of look at the counterexample that Moss writes down and any others that you can think of, the issue is sort of that there are too many congruences between the epsilon factors and characteristic 0, because when you mod out by L, I mean, you don't have access to L power roots of unity anymore. And so the idea, so Moss's idea is to try to recover these by basically enlarging the kind of rings that you have in order to include such roots of unity. So, okay, so what does Moss do? So basically, if you start with two, let me say, yeah, just irreducible generic representations of FL bar valued irreducible generic representations. Okay, so you want to define some sort of gamma factor for another, let's say generic representation to test against. So if I take tau, okay, I take tau, I guess, yeah, a representation. Well, how should I say this? Yeah, okay, let me say it this way. So you take tau tilde, which is going to sit inside of the Whittaker space of the, so okay, implicit in the background of all this is a fixed additive character, and you need to sometimes consider its inverse when defining the Whittaker models. But this is a fixed additive character, now FL bar valued, or more generally, R valued, where R is a local Artinian FL bar algebra. And you assume that this tau that you pick, or this tau tilde that you pick, if you specialize down to the ground field FL bar by killing the maximal ideal in R, this is isomorphic to the Whittaker model of tau. Yeah, I'm suppressing the character from the notation everywhere, but okay. So this is the kind of object that that Moss considers. You take your two representations over the ground field that you care about, but then you enlarge the kind of things you can test against in a way such that you can get sort of non-trivial roots of, like L power roots of 1 in these rings. Sorry? I don't think it requires that in the definition, but yeah. Yeah, thanks. Okay, so then using the using kind of the same argument. Well, I put same in quotes because I mean you have to check everything kind of works with general local Artinian coefficients, but there's no like serious obstacle. Using the same argument as in the Rankin-Selberg convolutions paper, you can define, well, you can define a gamma factor for this pair, like pi I and tau tilde, But now this thing is going to live inside of what I'll write as R double parentheses X. And by this, I just mean power series in the ring R with possibly finitely many negative coefficients. So it's not, yeah. And you do this in, yeah, I mean, again, the proof is sort of similar to the proof of in Rankin-Selberg convolutions in the sense that you take the Bernstein-Zelevinsky derivative formalism and apply more or less the same argument. Yeah, sorry. Well, okay, so yeah, that's a good point. So maybe I should put R here. Let me put R there for now. So the theorem that Moss then proves once you have these gamma factors is that they give you a converse theorem, but he proves the sort of optimal bound on the dimensions that you need of tau to test against. So let me write that a second. Right, so the theorem due to Gill is that, yeah, so if pi1 and pi2 are generic, well, irreducible, admissible, generic, admissible, generic, representations of, yeah, FL bar representations of GLN of F. And moreover, you know that gamma of pi1 and tau. Yeah, the other thing that maybe I should mention again is, in case it's confusing, is that the X there, like, so in the complex setting, this X again is a variable substitution that you can do, where you take Q to the minus S, which appears as sort of the determinant of G norm in the integral, and then you can factor it out, and then you can kind of cut up the group into pieces and then form a formal power series by taking the integral over all of each of these pieces, where the pieces are just matrices with like norm of determinant equal to blah. Okay, so yeah, I'm omitting X from the notation here, but there's an X there as a variable. So if you know that these two things are equal, for all, well, I guess all R, so in other words, all local Artinian FL bar algebras and all such tau, and for all R from 1 to this optimal bound, so the floor of n over 2. So I mean, yeah, the original theorem I stated was for n-1, but then okay, you can improve this, and Moss does take the optimal bound. Then, if all these hold, then pi1 is isomorphic to pi2. Okay, so this is yeah, so okay, so this is kind of the story in the context of local fields. Like when you've passed to this modular setting, you can define gamma factors in a naive way, but because there are too many congruences between them, if you lift and try to reduce and define it that way, you have to enlarge the kind of ring that you care about in order to capture the whole representation. Any questions? Cool. So in that case, let me switch to the setting that I actually care about, which is all of this over finite fields. Yeah, I mean, I don't know. This seems sort of backwards in that you'd expect something for finite fields might have been done before something for p-adic local fields, but here we are. Right, so let me switch to the setting of finite fields. So now I'm looking at FL bar representations of GLN of Q. And again, Q is a power of P, some prime, and P is not equal to L. So this is always in that setting. Okay, so briefly, the arguments that you use to define L and epsilon factors basically work in, so okay, let's start over C. So these work more or less in the same way and are in some ways somewhat simpler because you can define epsilon, well, yeah, let me say, you can define L factors, which turn out to just be 1, so we can ignore them. So you can define gamma factors using integrals. Well, okay, they're not integrals anymore, they're just finite sums. So you can define them using sums of the form. Well, again, just in the n-1 case, it'll look something like this. So you take GLM-1 of FQ, and then look at you quotient out by the unipotent radical of the Borel, and then you basically write the same expression, but now you don't have to worry about measures or norm characters or anything. It's just, you can, yeah. So I mean, you pick sort of two generic representations. In this case, I guess one of dimension n and one of dimension n-1, and then you assume they're generic, take a Whittaker model, and then you can define these sums. And using these sums and again, using like a finite field kind of analog of the Bernstein-Zelevinsky derivative functors formalism, you can prove that there exist gamma factors in the same way. And so converse theorems also exist in this setting. So for instance, for n equals 2, this is done by in some lecture notes by Piatetski Shapiro, and he also gives a really like a sort of nice formula for the gamma factor that you can literally just plug into a computer and actually compute these things using some very simple to write down Gauss sums, which was useful for us. For general n, this is done by Roditi. And this is done for, I guess, representations, well, maybe I'll say for tau of dimension 1 up to n-1. But as in the p-adic local field case, this is not an optimal bound, and Nien has a proof without going above n/2. Tau of dimension 1 to lower of n/2. Okay, so yeah, so things sort of remain simple in the complex case, as you might expect. So let me talk about the modular setting in this case. Yeah, here you just have a constant. Yes, exactly. Yeah. And it's just a number now. It's no longer like a formal power series with Laurent tails. It's just a number. There should be a compatibility in that if you take the power series and you plug in like well, yeah, if you take the power series, assume it has no poles, and then plug in like q to the minus s, then you should recover, well, for certain representation, maybe depth 0 representations, you should recover these gamma factors. But yeah, I haven't checked this so carefully. So yeah, I mean, I haven't really mentioned, like, the motivation for the beginning of the talk was to characterize some sort of correspondence, like a Langlands correspondence. And okay, there is some analogous thing in the finite field setting, which I haven't mentioned yet, but I'll say something about it at the end. Yeah, so, okay, so, right, what about the modular setting? Oh, yeah, I guess I didn't really, okay. Yeah, so modular setting. So again, FL bar valued representations. So in this case, it's again pretty easy to write down counterexamples to a naive converse theorem. So okay, remark again, the existence of gamma factors it sort of follows again the arguments of Jacquet, Piatetski, Shapiro, and Shalika. There is some complication in that for certain pairs of representations, which are called exceptional, you can't define gamma factors because the space of forms is too big, which does cause a sort of a problem, except that cuspidals, which you ultimately care about characterizing, have no exceptional representation. So this doesn't actually cause much of a problem, but it does slightly change the, like you need more assumptions in order to get such a definition. So let me just modulo removing some exceptional. And you can ask me later if you want a definition of exceptional, but let me skip it for now. Okay. And right, so okay, but then as before, I mean, this is sort of the analog of what Karinchuk and Matrange do, but there are pretty easy counterexamples to showing that this is not something that characterizes a correspondence, or sorry, does not give you a converse theorem. And the example is sort of similar to what Moss does. So if you take n equals 2 again, take Q to be P, which is 5, and then you take L to be 2. So again, in the sort of simplest possible situation, you can define two representations which have the same gamma factor, and this really just boils down to like a very straightforward Gauss sum computation once you use Piatetski-Shapiro's nice formula for these factors. So the two representations, how do you construct them? One of them, you can take the units in F25 and then map them to F2 bar by just taking a generator to a third root of unity. Okay, and then this gives rise, this is sort of in general position, so it gives rise to a cuspidal representation pi theta of, so yeah, this is irreducible cuspidal representation of, I guess, GL2 of F5 now. Okay, and then you can, right, and you can, and sort of knowing that it's induced in this way, you can compute its gamma factor fairly straightforwardly. The other thing you can do is you can take the induction from B to G. So G here is, yeah, sorry, G is GLN of FQ still. Okay, GL2 of F5, sorry. Of the trivial character, which since we are under the assumption where L divides Q minus 1, so Q is 1 mod L, normally this would decompose as like an irreducible and a Steinberg piece, but the Steinberg piece splits up, and so you get a composition series of blank 3, and you get 2 trivials and 1 sort of special representation. And that's a cuspidal representation. So this has a subquotient, which I'll call SP2, which is not, which is cuspidal. So it's not supercuspidal because it appears in this induction, but it is nevertheless cuspidal. And if you take any character of F5 cross and you follow this recipe, define the gamma factors, plug in both of these, then you get the same thing for all the twists. And so, okay, this is like a counterexample. And I mean, a remark, we don't have, so this is not the only counterexample. We don't have a full characterization of like every single possible pair of things that will give you one, but we do. But I mean, since in the n equals 2 case, you have a very nice formula for the gamma factors that you can just plug into a computer and see what they are. We have other examples. I mean, L is a relatively small number in terms of computational power, but so yeah, this is, I mean, yeah, we have evidence for the fact that you need to really do something to fix this problem. Cool. So, right. Okay, so this is the setting that we're working in. So let me state what we do. So I guess like an overview of what we do is that we do something very similar to what Gill does in the modular setting for p-adic local fields, except that we significantly reduce the number of local Artinian algebras that you need to consider to get to actually get a converse theorem. So the theorem, well, there's too many letters. I can't remember them all. So let me just say our theorem. So if you assume pi1 and pi2 are two irreducible generic, and for now we need cuspidal representations, although it should probably hold more generally, of GLN of FQ. And if you assume that, right, I should say FL bar representations. These are in the modular setting. And if you assume that tau is a so for us, we just need n-1. So if it's an irreducible generic representation, well, yeah, again, FL bar. Representation of GLN-1 FQ. Okay, then the first thing we do is define a gamma factor of pairs, but well, okay, let me introduce some notation first before I say what those actually end up being. So let p tau denote the projective envelope of tau in the category of like FL bar GLN-1 modules. So and then let R tau denote the endomorphism ring over the same category. So just of p tau. Okay, so tau is assumed generic, and so we take the projective envelope of this thing, and then we take its endomorphisms. This is the commutative local Artin ring. Artinian FL bar algebra. So for instance, if you're in the case of n=1, this ends up being basically the group ring of, well, if you're in the case of n=1 and you assume that L divides, or some power of L divides Q-1, then this ends up being sort of the group ring over FL bar of the L part of the units or well, yeah, the L part of the units in FQ. So I mean, this, which sort of, yeah, I mean, it's sort of the same thing where you're missing L power roots of unity and you sort of add them back in by adding these rings, but which, yeah, in the n=1 case, you can see are doing exactly this. Okay, so what we do is we then define a gamma factor basically for the pair. Well, okay, either one of these pi's, so pi1 or pi2, and then now really the projective envelope of tau, but working with well, R tau coefficients. So you sort of base change everything to R tau and then work with the Whittaker space there. Like, I guess the heart of the argument is showing that this thing kind of sits inside of that Whittaker space and is sort of split. The map to the Whittaker space is split, the natural one. And so then you get a gamma factor, which is gamma, I guess I'll call it gamma tilde pi I times tau, which lives now inside of, well, the units of this endomorphism ring. Okay, it's not the end of the theorem. We just switch boards. The point is that we then use this to prove a converse theorem. So, right. Yeah, so again, the definition of the gamma factor is, again, it's very similar in spirit to, like, I mean, the proof that it exists is similar to what Jacquet, Piatetski, Shapiro, and Shalika do, but again, we have to be careful with this this notion of exceptional representations, which is something that I guess is not really done in the previous work because they just restrict to the setting of cuspidal representations where you don't have any exceptional things. But I mean, we define the gamma factors in like, I mean, really the gamma factors we define are things living over like z1 over p, mu p, infinity of, I guess, well, yeah, mu p infinity, let me just say. Yeah, so we define gamma factors over some general class of rings and do it for any like representations which are of Whittaker type, but let me not talk about this. So right, then the point is that if you show that this like modified gamma factor against tau is the same for both pi 1 and pi 2. And so now this, I mean, this is an equality. I mean, when you vary this tau, the ring that this equality is taking place in is changing every single time. Although they all sort of sit in the endomorphism ring of the Whittaker space in some sense. For all such tau, so for all irreducible generic tau, then these two representations are isomorphic. Okay. Yeah, and I guess right. So I mean, how does the proof go? I mean, the proof, again, the construction of the gamma factors is it's following the Rankin-Selberg convolutions method, reinterpreted to use like Bernstein-Zolovinsky theory. And it's a little more work because we work over a general class of rings, which has some technicalities, but nothing too horrible. Then yeah, I guess the second step is to basically show that when you how do I say this? The second step is to show what we call what's called a completeness of Whittaker model statement, which in the p-adic setting is usually called L2 completeness of Whittaker models. So this is kind of the key ingredient, which says that, so it's a lemma, but it really, like in the proof of the lemma, you kind of see why you need to work with these more general rings instead of just FL bar, because otherwise you can't sort of access the whole Whittaker model in some sense. But it says that if you start with any Whittaker function for FL bar, so take a non-trivial additive character of FQ and then inflate it to the unipotent and then induce it to get the Whittaker space. So if you start with any function and you can pair it against like every Whittaker function ranging over all all Whittaker functions inside of the Whittaker models of these p taus, but now where p tau is viewed as a representation with coefficients in its endomorphism ring. So you have to sort of, justify why you can like, why this thing is sort of generic in the sense that it embeds into its Whittaker model. Okay, and for all tau, irreducible generic, then this function is 0, and so I mean, the rest of the proof is basically the lemma plus a standard argument. Sorry, let me move this up. Lemma plus a standard argument shows that actually the Whittaker models of pi1 and the Whittaker and pi2 are sort of equal in the Whittaker space, and so you're done. Okay, so that's kind of that's sort of what we do, and then yeah, I mean something that we haven't done but are thinking about doing is trying to show that this type of gamma factor actually characterizes some correspondence. So there's this thing called there's the finite field analog of the local Langlands correspondence it's proven by McDonald in the 70s. So I guess you call it the McDonald correspondence. And the McDonald correspondence basically goes from irreducible reps. Well, I mean, okay, he does this over the complex numbers, but irreducible representations of GLN of FQ, and then relates and then shows that they're in bijection with tame irreducible representations of the Weil group up to inertial equivalence. So in other words, you just forget about Frobenius. I mean, two things are equivalent if they're equivalent on inertia. And this is the kind of correspondence that you might expect these sort of gamma factors to characterize. They are also compatible with, I mean, in the complex setting, these are compatible with like the depth zero local Langlands correspondence. So if you put like representations of GLN of, okay, some field with residue field FQ, which are depth zero, and then you look at the tame irreducibles, but don't take inertial equivalence, then there's like a commuting diagram that you can draw. And so, I mean, one thing you could do is you could try to characterize this correspondence by lifting and then using the characterization of this correspondence to kind of reduce it to here, and you can do that. But I don't know. Sort of the goal of, I mean, like one of the things that you can do once you've set up gamma factors in this setting is you can imagine a mod L version of this, and imagine trying to characterize it, maybe following the proofs of Iyengar or Jacquet. And maybe I'll briefly mention that Tsujan Lee and LiShotton have proven some kind of mod L analog of, well, they've proven some statement which you can use to deduce a mod L version of the McDonald correspondence. And so something that we, I think, want to do is prove that this correspondence could be characterized by these slightly more general gamma factors. So I think I'm basically out of time. So thank you.